So we've talked about cyclotron motion, and that was referring to charged particles going in circles in a magnetic field. Now there's a device called the cyclotron. So this is a thing where before cyclotron motion is a concept. And so the cyclotron is a type of particle accelerator. And I'm going to talk you through it, but it's one of those things that's kind of a special scenario that maybe you'll see a calculation on it, but it's not the most important thing in the chapter. So the idea is that we have a couple of pieces here. We have a uniform magnetic field, and that is coming from two magnets. Note that this is the bottom magnet. There's a top magnet too, but you basically don't see that. So there is a top magnet, there's a bottom magnet, and between them you get roughly a uniform magnetic field. So now the second thing is that we have an oscillating accelerating potential. So remember that this is a potential, and that's coming over here. So we use this symbol if it's an oscillating potential. So this isn't a battery. This is something like a signal generator or the type of electricity that comes out of the wall. We haven't otherwise talked about oscillating potentials, but this is like a sine wave. It goes up and down. So what is that actually connected to? Well, that potential is actually connected to what are called Ds. And the Ds, well, they look like the letter D, so that's where the name comes from. But the idea is that these are just metal boxes that are semicircular shaped, and what we're doing is putting a potential difference between them. And so think about what's happening on the inside here. Basically, on the inside, we're getting a parallel plate capacitor. Not exactly, but something close to it. Why? Because if you notice, we have two surfaces that are parallel and have that potential difference across them. So we're injecting protons into this. We're putting some charged particles into this, and they actually can pass between these two metal plates. And every time they're in between the metal plates, they have that accelerating potential, and they get accelerated. They feel that electric field, which creates a force and accelerates them. Why does it need to accelerate? Well, sometimes they're passing from the right D into the left D, then they're going to pass from the left D into the right D. So sometimes you need to accelerate them to the left, sometimes you need to accelerate them to the right. Now, how do we set up the magic to actually make that happen? The frequency stays constant. Why? If you go back a few videos to the cyclotron frequency, we saw that that didn't depend on velocity. That depended on the mass of our particle, the charge of our particle, and the magnetic field. But so what's nice about this is we know that the frequency of our oscillating potential is simply the cyclotron frequency. That our particles are basically sloshing back and forth in the circle at a given frequency no matter what their speed is. So we simply slosh the potential back and forth at the same frequency. Now, as they hit that gap and accelerate a little bit, the speed is going to increase. Now remember that the radius, so the cyclotron radius, does depend on speed. So that's why it circles from little circles, and then you get bigger circles and bigger circles. So every time it accelerates, it goes into a slightly bigger circle, and the speed can keep increasing that way, the radius keeps increasing. Eventually, the protons exit, and they have some pretty big final speed, even though they started almost at rest. So this is a compact way to accelerate particles. Now, this is literally a way that particle physicists used to accelerate particles. Nowadays, we have other techniques, but cyclotrons still exist. Now, you might say, well, who cares? Why do I need to accelerate particles? Well, once upon a time, we were trying to actually understand what make up atoms, right? What are protons? What are neutrons? Nowadays, we're trying to understand what are quarks, and we need to use accelerators with way more energy than what we can do with this. However, we still use cyclotrons for other things. So for instance, you need small accelerators to create radioactive isotopes that get used for cancer imaging and therapy. So you might have small accelerators like this in a hospital to actually make radiotherapeutic drugs. You might also have cyclotrons for making special materials for doing radiation hardening of materials. We can do imaging with these, though typically when we're doing imaging or radiation therapy, we use other types of accelerators. But it's important to know that accelerating particles has a lot of benefits besides just fundamental particle physics.